Hello everyone. Can someone please confirm if you can hear me and see me? Okay, great. So I'm going to be teaching today's class of basic and intermediate number theory. So let's go. So who am I? I am Surya, uh, and I'm going to be introducing myself in this next slide. So my biggest achievement in competitive programming is I was twice ACM ICPC World Finalist in 2014 and 15, and I have been most active during 2011 and 2016. Uh, Pretty old guy in the competitive programming community. So, what's my work experience? I worked in Google for 4 years, 3 years in US and 1 year in London. And last January, I quit my job to start working on my own startup. And where did I study? I studied in IIT Roorkee. I did bachelor's in electronics and communication. Teaching experience. Sorry for that. I taught much in my college time. Like to my juniors, we used to have a programming group where seniors used to organize lectures for juniors and all. So I taught there, and I taught in few programming camps as well. So probably the biggest question is, what are we going to do today? So this is the objective. Looks like very big, isn't it? Lot of new names for some people, maybe. So we are going to. Don't worry, these are all very simple topics. Like each one is very simple. Like we'll go one by one, and you will learn each thing in detail. Uh, so. Uh, One thing is, everybody comfortable in English? Oh, no, no, no. Okay, great. Um, okay, cool. Uh, so yeah, we are going to first start with basics of modular arithmetics. Like in number theory, a lot of things are done using the modular operation. So we are going to learn the basics of that, and we are going to learn about Euclid's theorem for finding GCD. We are also going to look at some Bezot's theorem, extended Euclid's algorithm. We are also going to learn about linear Diophantine equations. Uh, we are also going to learn about inverse modulo, Chinese remainder theorem, Euler totient function, and Fermat steady theorem. So let's go one by one. So is my voice not audible? Somebody just said in the chat it was not audible. Is my voice not? It's audible. Okay. Please check. If somebody can't hear, please check. So let's start. So before starting, please note that two important points. The first one is, we are only going to be dealing with integers. We are not going to talk about real numbers or rational numbers or any decimals or complex numbers, nothing. It's simple. We are only going to deal with integers. So we are also only going to deal with addition, multiplication, subtraction, division, and modular operation. Simple, right? Nothing complex. We are not going to use any kind of complex notations or random complex theories or convergences or anything. Simple. Almost all of you know the first four operations, right? Addition, multiplication, subtraction, and division. Everybody knows that. We learned that in elementary maths. Modular operation, some people might not know that because it's something that comes at college level. So some people might not know that yet. Most of you probably already know that. So let's go. So what is a modular operation? A modular operation is the remainder you get after dividing with n. Simple, right? Nothing complex. If you have two numbers a and n, a mod n is just the remainder you get after you divide it with n. Suppose a equals to 10, n equals to 6. What is the remainder we get after we divide? A mod n will be 4. Simple, right? Like that's it. Basically, that's it. Nothing complex. Like if we represent a as k into n plus r, then a mod n equals to r. As simple as that. Nothing complex. So let's go to the next one. We are going to look at modular representation. Like when we are writing equations and all, right? Like writing something like this solves a lot of problems. Trust me, in future slides, we are going to use this kind of notation a lot. So if a equals to kn plus b, then a mod n equals to b. We just saw in the previous slide. Then we write this notation as a equal to b mod n. Okay. So we are also going to look at integer factors. If you think that this is going really slow, please wait. Like the things will improve. I'm just trying to cover from very basics, like really good basics. We have 2 hours of class. We are going to look at some interesting topics as well. Like once we have all the basics covered, then we build up on the basics fundamentals, or we build some concepts over this. And one if the basics are not clear, then it will be hard to understand those. So what are integer factors? Suppose we have a number n equals to 10. This can be represented as 2 into 5. 2 and 5 are integer factors. Like all the numbers that are less than n, which are divisible by n. So the integer factors of n are 1, 2, 5, and 10. These are the integer factors of n. Or basically any number a such that n mod a equals to 0 is called an integer factor. When you divide n with a, the remainder is 0. That is a divisor or integer factor. Or a equals to 0 mod n. We just learned this notation before, right? Yay! So we used it already. So what is GCD of a pair of integers? GCD is the greatest common divisor of a pair of integers. Like you have a, you have b, you have p1, p2, p3, so on up to pk, the divisors of a, and q1, q2, q3, so on up to ql, the divisors of b. The divisor sum x, which is present in this and this set, the largest such x is called GCD. X equals to 0 mod, a equals to 0 mod x, a percentage x is 0, b equals to 0 mod x. The largest such x is called the GCD. A mod x equals 0, b mod x equals to 0. Cool, got it. This notation is just simple dxt. It's a mod x is the remainder you get after dividing with x. this one I think I made a mistake here. It's mod a, n equals to 0 mod a. Okay, let's go. What are coprimes? You have two integers a and b. Two numbers are called coprimes if GCD of a comma b equals to 1. Simple, right? That's it. They are coprimes. Two numbers are coprimes if GCD of them is 1. They don't have any common divisor. Are 21 and 36 coprimes? Okay, cool. Got it. The answer was no. So, question. Does anybody have any questions for the class so far? Please post it in the questions sections. If anybody has. What was x there in the GCD one? X is the largest integer where n. Okay, can it be a little faster? Sure. Sorry for the delay. So x is the largest integer where a is equal to 0 mod x and b equal to 0 mod x. That's it. X is the largest integer. Somebody asked that. Cool. As nobody has any more questions, let's go further. We go to Euclid's theorem to find GCD. Given two integers a comma b, we have to find their GCD. So how are you going to do that? Suppose a is less than b, then GCD of a b is same as GCD of a comma b mod a. Why is this true? Suppose b equals to k into a plus r. Okay, then the GCD of b comma a, if it's d, if it is equals to d, then what is b mod d? Equals to 0. That means k into a plus r mod d equals to 0. That is, since a mod d is 0, we just get r mod d equals to 0. So d is also a divisor of r. D is also a factor of r. So since d is also a factor of r, we just get GCD of a comma r same as GCD of a comma b. So you may ask, what if GCD of a comma r greater than d? If we have such greater than d, like let's say GCD of a comma r let's say GCD of a comma r equals to k, then b equals to sorry, not k, let's use some other range, p. If GCD of a comma r equal to p, then b equals to ka plus r. That equals to k into, since p is a divisor of a, we can write it as some x into p, r we can write it as y into p. So p is also a divisor of b. P is also a factor of b. So suppose we are trying to find GCD of 24 and 18. We find recursively, since a is greater than b, we just swap it. What is a here? A is 18. We recursively find GCD of 18 comma, because GCD of 18 comma 24 mod 18 is 6, and again we swap a and b as a is less than b, we supposed. This will be 6 comma 18 mod 6 is 0, so the GCD is equal, 6 comma 0 is 6, so GCD of 24 comma 18 will be 6. So this is true because suppose let's say GCD of, suppose let's say B equals to KA plus R. Then B mod A is R. Suppose GCD of A comma R is P. Since GCD of A comma R is P, we can write A as X into P, R as Y into P. Okay, since P is a divisor of both A and R, we can write A as X into P, R as Y into P. So B equals to Ka plus R. So we can write K into X into P plus Y into P, and we can take P outside and it will be P into Kx plus Y. So P is also a divisor of B. So GCD of A comma R divides B. And we also have to find GCD of A comma B also divides R. Let's say GCD of A comma B is equals to D, then K into A plus R equals to D. So since K into A is a multiple of D, R should also be a multiple of D. Okay, so that's why we have D dividing R. So let's, does anybody have any questions on this so far? Can you repeat it? Okay. I'll quickly repeat it because it might be a little slow for others. Suppose we need to find GCD of A comma B, and let's say A is less than B. Then GCD of A comma B will be equal to GCD of A comma B mod A. This is because, let us say this is equals to D, some number D. Since GCD of A comma B equal to D, D is a divisor of B. B can be written as some I into D. A can be written as some J into D. So B is also equal to K into A plus R. So K into A plus R mod D should be equal to 0. This is because D is a divisor of B. Since D divides B, this is should be the remainder should be 0. Since A also divides B, this is K JD plus R in mod D equals to 0. KJD mod D is already 0, so we get R mod D equals to 0. So D is a divisor of R as well. So we get A comma R, the greatest common divisor. If we take, we get the GCD of A comma B. Let's go to the next slide. Bezout's identity. The name looks very complex, crazy, but it's very simple. If there are two integers A and B whose greatest common divisor is D, then there exist integers x and y such that ax plus by equals to d. I hope everybody understands this. I'll repeat. If there are two integers a and b with GCD d, then there exist two pair of integers x and y such that ax plus by equal to d. Yes. Soon we'll see how to prove this, Vaibhav. Let's go. Let's say the question itself is, let's try to find the integers x and y. There is an algorithm given by Euclid, which is called extended Euclid's algorithm, to find such integers x and y, such that ax plus by equals to GCD of a comma b. How is that? Suppose, let's say we already found the solution for b mod a and a, which is x1 and y1. Then we have b mod a into x1 plus a into y1 equal to GCD of B mod A comma A. This is basically the Bezot's identity, right? Like AX plus BY equal to GCD of A comma B. Suppose we already found x1 and y1 for B mod A comma A, which are x1 and y1. Then we have this Bezot's identity written as those. Now next, let's say B equals to K into A plus B mod A. We already know this notation, right? Like we just saw before. Then we have B mod A plus K into x1, Ka plus x1, and A into y1 minus K into x1. Like basically Ka x1 minus Ka x1, we just add and subtract. Okay. Then we have the same equation here, right? We have this equation. We just add and subtract K into A into x1 to this equation. K into A into x1 term here, K into A into x1 term here. Here it's subtracted, here it's added. We have the same equation. So basically this term can be represented as y2 and this is represented as B, and this can be represented as x2. So we can find x2 and y2 using x1 and y1 this method. So what we had here is this equation. Let's say B mod A equals to B equals to Ka plus R. Okay. B equals to Ka plus R. Then we already know the equation answer for R into x1 plus A into y1 equals to GCD, which is G. Let's just write GCD as G. Since we know that GCD of B mod A and A equal to GCD of A comma B, let's say they both are equal to G, then we recursively solve for R and A, which is x1 and y1. R into x1 plus A into y1 equals to G. Then we add and subtract Ka x1. R x1 plus Ka x1 minus Ka x1 plus A y1 equals to G. Then we take x1 common of this, x1 into R plus Ka plus, we take A common from this, A into y1 minus kx1 equals to G. So this is equal to B. This is B into x1 plus A into y. Let's call this term as y2 equals to G. Let's call x1 is equal to x2. Then this will be bx2 plus A y2 equal to G, where x1 equals to x2 and y2 equals to y1 minus kx1. I hope this is clear now. Like using x1 and y1, we find x2 and y2 using these formulas. So let's go next. Is it clear? Let me have a poll. Is it clear? Somebody, let's please answer this poll. If it's not clear for more than 75%, I'll try to explain it again. Okay. Half of the people said it's not clear. Okay. So, okay, clear. Manas is just saying that clear, but he doesn't think he'll remain it for a long time. It's simple, Manas. Like, try to write it on your own in a paper. Then you can remember it. Like, it's nothing to remember. Like, it's very simple. Like, we can write b as k into a plus r. Okay, like, let's say uh, b equals to some 21 and a equals to 5. Then we can write b as 20 plus 1, 21 as 20 plus 1, that is equals to 4 into 5 plus 1, that is equals to k into a plus r. R is 1 here, k is 4 here. So we have to find the x and y for a and b. For this, we try to find x and y for r and a first. Let's try to find x and y for r and a first. Then using x1 and y1, we try to find x and y for a and b. First we find x and y for a and r. Then using them, we find x and y for a and b. So let's say x1 and y1 are the pair for r and a and r. Let's say GCD is equals to G. Then we add and subtract k a x1. If we just add and subtract, the right hand side and left hand side still remain the same, right? So we take x1 common from these two terms and a common from these two terms. So x1 into r plus ka, a into y minus kx1, that equals to G. This one equals to b, bx1 plus a. Let's write this term as y2, a y2 equals to G. So x2 will be equal to x1 and y2 will be equal to y1 minus kx1. So using x1 and y1, we find x2 and y2, which are the x and y for a and b. I hope this is clear. Let me go to the let me ask, like, is it clear for everybody? Please answer this poll. If it's clear, then we'll move on to the next step, or else I'll quickly do something and okay, it's clear for a lot of people, so let's go. You don't need to you don't need to remember the whole process. You just need to remember that it is possible to find such an x and y for a and b equals to G. Ax plus by equal to G. Linear Diophantine equations. Any equation of this form is called linear Diophantine equation. Okay, simple, nothing complex. Anshul just asked, isn't y2 equal to x1? Oh yes, yes. I might have confused x1 and y1 there, but yeah, you are right. y2 is equal to x1. True. Equations of this form are called linear Diophantine equations. So given a, b, c, we have to find x and y for any a and b and c. When is this true? This can be true only when GCD of a comma b equals to c, right? So, oh no, it's GCD of a comma b is a divisor of c. Only then the solution exists. Why? If GCD of A comma B, if it's equals to G, then we already know that we can write AX, oh no, GCD of A comma B is equal to G, then A equals to some P into G, B equals to some Q into G, then we have AX plus BY as equal to C. This is equal to P into GX plus Q into GY equal to C. Then we take G common outside, G equals G into PX plus QY equal to C. Right? So G is a factor of C. What I just wrote, just writing with text here. So, any questions? What if GCD of A comma B by K? Then GCD is not a factor of C, right? It can't be possible. Okay, nobody has. GCD of A comma B is a multiple of C. It's not a multiple of C, it's a divisor of C. How does it prove the theorem? That was previous question. Okay. So somebody asked to show the previous slide. Somebody is asking where are we going to use these concepts? Good question, Ayush. These are fundamentals of number theory. Once you know the fundamentals, we'll try to solve some actual problems in CodeChef using these problems. So there are a lot of number theory problems in CodeChef. So in competitive programming, using these concepts, there are a lot of problems. How come two numbers larger than GCD end up adding to it? That's a very good question. Larger than GCD end up adding to GCD. This can be possible only if one of these two numbers is a negative number, right? If y is negative, then we can get some number like less than a and b, right? Like we just saw in the previous slide. Here we are writing y1 minus kx1, right? If y1 is less than kx1, then this number will be negative. The x2 will be negative. Y minus kx1. y1 minus kx1. This number will be negative. C is GCD of A comma B. True. Yes, you got that right. That's actually true. Aman, if C can be a multiple of GCD, that's actually the point. Because if C is a multiple of GCD, like let's say C equals to G into K. Okay. then we already know how to write ax plus by equal to g, right? Using Euclid's theorem, we just found how to do that. Then we just multiply k on both sides. Then it will be a xk plus b yk equal to c. Like if c, the only requirement is c should be a multiple of g. Any more questions? Negative numbers, yes. If negative numbers, we can just x and y, if we just multiply minus, so the question was, if 3x plus 2y equal to minus 1. Yes, this can be possible. Our x and y are integers, so x and y can be negative numbers. So 3 into minus 1 plus 2 into 1 equals to minus 3 plus 2, that equals to minus 1, right? So we can find x and y for 3 and 2. Okay, so let's move. We are also going to learn about inverse modulo. Cover a couple of questions. Yes, I was planning to cover the questions at the end. So if you can wait a little bit more, we will cover those questions. So inverse modulo. So if two numbers a and b, if a into b equal to 1 mod m, then b is called a inverse. That's it. Simple, right? Nothing complex. We already note this notation, like if a b mod m equal to 1, then b equal a inverse, or a is called b inverse. B inverse equal to a. So how do we find the inverse? So okay, somebody is asking for an example. So example is this, like let's say m is equal to 5, a equals to 2, b equals to 3. What is a into b? That equals to 6. That equals to 1 mod 5. Right? If we divide 6 with 5, we get 1 mod 5. So 2 inverse is 3. 3 inverse is 2. Mod 5. We should always write mod 5. So isn't m always a into b? I did not understand your question, Priyank. Is there any restriction for m here? We'll find out. What are the criteria? Like there exists an inverse a into a inverse equal to 1 mod m. We'll try to find the criteria sooner. If b is greater than m, it is just, we just take the remainder of b, right? Like why is 6 equal to 1 mod 5? It's it like you must go to the previous part of the lecture. Oishik, if I did not pronounce it wrong. 5 mod 2 inverse equal to 3. No, not Vaibhav. It's 2 inverse mod 5 equal to 3. 2 inverse mod 5 equal to 3. 2 inverse percentage 5 equal to 3. So let's go. How to find inverse modulo? It's using extended Euclid's algorithm. Simple. We already learned a very useful algorithm. We'll try to use it and find the inverse modulo. Okay, this is, we assume that A and M are co-prime. An inverse of A mod M exists only when A and M are co-prime. The GCD of A and M are 1. Like let's try to write AX plus MY equal to GCD of A comma M, right? If we divide M on both sides, M mod Y is equal to 0, we get A into X equals to 1. So X will be the inverse of A. So okay, why is it true that A into B mod M equal to 1 only when A and M are co-prime? I'll give you 2 minutes to think by yourself why this is true. If A and M are not co-prime, then B doesn't exist. There is no such B. This is because, let us say A equals to some number P into G, where G equals to GCD of A comma M. Okay, if G is greater than 1, then we write A equals to P into G. Since A into B mod M is equal to 1, A into B equals to some Km plus 1, right? Let us say M is equals to some Q into G, okay, where G is the GCD of A and M. Now A into B is equal to Km plus 1. Let us prove by contradiction. Let us say there exists some B where A into B equal to K into M plus 1. Then we try to divide G on both sides. A into B mod G is equal to 0, right? Since G is a divisor of A into B, since A is a multiple of G, A into B is also a multiple of G, this will be equal to 0. But the right hand side, Km plus 1 mod G, this will be equal to 1. This is because Km mod G equals to 0. So LHS will be equal to 0 and RHS will be equal to 1. This can't be possible, right? So that's why there doesn't exist any such B where Km plus 1 equal to AB if GCD is greater than 1. So that's why, since GCD is equal to 1, A and M are co-prime. So since A and M are co-prime, we already know that we can find X and Y using Euclid's extended algorithm. So if we divide M on both sides, we take modulo M on both sides, we'll get AX equal to 1 mod M. So X will be our inverse of A. Let's go to the next step. Any questions? Yes, yes, Ricky, we can use totient function by Euler. We are going to find about it later. When is the workshop? I don't know what workshop you're asking, user. Thanks, Rahul. Okay, looks like there aren't any questions. Okay, I'll be covering explanation for totient function, Vicky. Don't worry. We are going to learn that today. So now we are going to learn about a really interesting theorem called Chinese remainder theorem. Chinese remainder theorem. This is a very interesting theorem. There are why Chinese? Because it was invented in China a long time ago, so that's why it got Chinese remainder theorem. Uh, so there are a lot of problems on CodeChef which can be solved using Chinese remainder theorem. So let's try to learn that. Let n1 to nk be k integers greater than 1. Let us say there are k integers which are greater than 1. Let us denote their product with capital N. The product of n1, n2, n3, so on up to nk, it is capital N. And the Chinese remainder theorem asserts that if all the ni are co-prime pairwise, that means GCD of ni and nj equals to 1 for all I and j, and if a1 to ak are the integers such that 0 less than ai less than n for every I, then there exists only one integer x such that 0 less than x less than n, where x equal to ai mod n. In simple terms, we have x equals to a1 mod n1 Sorry for the handwriting. I don't know why my pen is not working very well. A2 mod N2 so on up to AK mod NK, then there exists only one such x from 0 to n. From 0 to capital N, from 0 to capital M, there exists only one such x, such that if we are given a12 to ak and n1 to nk, x equal to a1 mod n1, x equal to a2 mod n2, changing it, ak mod nk. Okay, there exists only one such x. Why this is true? Let's try to find out. Let's try to prove this. Let us try to find in case of two integers. Let's say k equal to 2, the whole the system here, like let's solve it for k equal to 2. X equal to a1 mod n1, x equal to a2 mod n2. We try to find such x where x less than n1 n2, 0 less than or equal to. We try to find that there exists such an x given a1 a2 n1 n2. There exists such x where 0 less than or equal to x and n1 n2. We try to find such x. Since we already know that n1 and n2 are pairwise coprime, using Euclid's extended algorithm, we can find m1 and m2, right? Is equal to GCD of n1 and n2, right? So, since we can find this using Euclid's extended algorithm, find the pair m1 and n2, then x can be given with this equation. X can be given with this equation. Let's try to prove this. Let us write, since m1 n1 m2 n2 plus m1 n1 equal to 1, m2 n2 can be rewritten as 1 minus m1 n1, right? Since m1 n1 plus m2 n2 is equal to 1, this we found using Euclid's extended algorithm. Bezout's identity states that such m1 and m2 exist. We try to write x as this number, then a1 plus m2 n2 plus a2 plus m1 m1. Since m2 n2 is equal to 1 minus m1 n1, we just substitute that in place of m2 n2. Then we get a1 plus a2 minus a1 into m1 m1. We just take common m1 n1. Now if we take modulo n1, we get a1. Since this term will be equal to 0 if we divide by n. Okay. There are a couple of questions in the chat. How this equation x equal to a1 m2 m, this is a tricky question. Like based on observations, let's suppose we found it. We found such an x where a1 m2 n2. Arjun has asked, how did you get the equation m1 n1 plus m2 n2 equal to 1? We already found this, right? Ax plus by equals to GCD of a comma b. We already know that this can be solved using Euclid's extended algorithm, right? Since a and b are co-prime here, A and B are n1 and n2, since GCD is 1, the right hand side is 1. So that way, if we take modulo n1, we get a1. We can prove in a similar way that we get a2 if we take modulo n2. So hence we found such x. A and B are co-prime. Yeah, here A and B are in n1 and n2. In this equation ax plus by equal to g, here the equation is m1 plus n1 equal to 1. n1 and n2 are co-prime, not m1 and m2. n1 and n2 are co-prime. How to find m1 and m2? We just discussed Euclid's extended algorithm, Akash. You can go back in the video and watch that. How is x written in such a way? Let's suppose there is an x which is written like this. Then such an x is a solution for these equations. So there's that. How is a1 percentage n1 equal to 0? No, a1 percentage n1 is not equal to 0. X percentage n1 equal to a1. This is the equation. X mod n1 equal to a1. This representation means this. In the beginning of our class, we discussed that. How do we know that RHS of the equation is less than the product of n1 and n2? Simple, Tejas. If it is not equal to that, we just divide it with n1 and n2 and we take out the remainder. We just take the remainder. We just divide it with n1 and n2. We just take out the quotient factor. Since this number mod n1 is equal to a1, x mod a1 is equal to n1, then x mod n1 n2 mod n1 will also be equal to a1. If a1 equal to a2 equal to x, CD conjunction is used, which is not necessary. If I am wrong, then please correct me. I did not understand your question, Kaushik. A1 equal to x mod n1. A1 is not equal to n1. Second equation. This one, are you asking? Or this one? M1, N1. Okay, this one. We just write that there exists such an x which is equal to a1 m2 n2 a2 m1 n1, and we try to prove that this number mod n1 is equal to a1, this number mod n2 is equal to a2. This number mod n1 we found that is equal to a1 because this term is divisible by n1. Then from the first equation, a1 is equal to a2 is equal to x. No, a1 is not equal to a2. A1 can be different from a2. Let's go further. We just found out for two integers n1 and n2. Are there any questions so far? Like, let me ask, like, does anybody have any questions in this? Let me create a poll. Should we is this clear or not? If it's clear, then press yes or true. If it's not clear, then press false. Okay, a lot of people it's clear. We'll proceed further. How to find for general case? Now that we found x for n1 and n2, let's say uh, y equal to x mod n1 n2 y equal to a3 mod n3. Then since for n1 and n2 we found x, since y, let's say y equal to x mod n1 and n2, then y mod n1 equal to x mod n1, that equal to a1 y mod n2 will be equal to x mod n2, that is equal to a2. So for this one we found x. For these two set of equations, let's say we found x, then we just need to find such a y for next two. So recursively, iteratively, we find y for a1, a2, a3, n1, n2, n3. So now that we have y, let's try to say there is some z equals to y mod n1, n2, n3, and z equals to a4 mod n4. So since let me go it again. Since we already found x mod n1 equal to a1, x mod n2 equal to a2, we found such an x less than n1 and n2. So we try to find for that x and n1 n2 pair and a3 and n3. Since we already know that x mod n1 equal to a, x mod n2 equal to a2, if we find such a y which is equal to x mod n1 and n2, that y will also satisfy these two equations. Okay, if we found a y which satisfies these two equations, x mod n1 n2, a3 mod n3, then that y will also satisfy these two equations. Okay, that way we recursively find for a4, we already know that n1, n2, n3, we already know the solution as y. For n1, n2, n3, n4, we find z using the previous slide. Is this clear for everyone? Is this clear? Select true if it is clear, or else I'll repeat that. Okay. Let me repeat this again then. Since let's say we already found some x, we already found an x for the first two a1 and a2. Okay, we already found an x for a1 and a2. We already found an x for a1 and a2. That x is less than n1 and n2. Now if we find y equal to x mod let me try to fix this. My pen tablet's pen is not working so great. I don't know the reason. X mod n1 n2 y equal to a3 mod n3. If we find an answer for these two equations, y equal to x mod n1 n2, y equal to a3 mod n3, then such a y also satisfies these two equations. Like there are k equations, right? X equal to a1 mod n1, x equals to a3 mod n3, like that. There were k equations, right? Like here there were k equations, x equal to ai mod ni, x equal to ai mod ni. We have k equations. For the first two equations, let's say we found an x. Let's say we found an x. We already found an x. Now using that x, we try to find a y. Y equal to x mod n1 and n2, y equal to a3 mod n3. Since n1 and n2, n1 into n2 is co-prime to n3, we already know that n1, n2, n3 are co-prime pairwise. n1, n2 is also co-prime to n3. We find y equal to x mod n1, n2, y equal to a3 mod n3. We find using this formula here. Then such a y will also satisfy the first two equations. So using such a y, we'll find z for a4. Like that, iteratively we find for ak. Is this clear? Select it true if it is clear. Okay, great. Looks like it's clear for a lot of people, so let's move on. Do you have any questions? Does anybody have any questions? Looks like no questions as well. Let's move on. Somebody asked it before, Euler totient function. Let's try to understand what is Euler totient function. So Euler totient function is number of integers less than n which are co-prime to n. Number of integers less than n. Let's say n equals to 10. Out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of all these numbers, the number of numbers which are co-prime to 10, what are those numbers? 1, 3, 7 and 9. We have 4. So 5 of 10 is equal to 4. 5, the GCD of 5 and 10 is 5, right? So it's not 1. So 5 is not a coprime. 1 is a coprime, yes. 1, GCD of 1 and 10 is 1. The GCD of 1 and 10 is 1. GCD of 2 and 10 is 2. 3 and 10 is 1. 4 and 10 is 2. 5 and 10 is 5. 6 and 10 is 2. 7 and 10 is 1. 8 and 10 is 2. 9 and 10 is 1. So all the numbers where GCD was 1, the count of those numbers is called Euler totient function. Phi of n. So let's go further. Total count is 5. How is it 5? It's 1, 2, 1, 3, 5. Oh, no, 1, 3, 7, 9, right? Only 4 numbers. Total count is 4. 1, 3, 7, and 9. So phi of AB is phi of A into phi of B. Phi, just looking at the chat, 1, 3, 5, 7, 9. 5 is not a coprime, right? 5 is a divisor of 10. GCD of 5 comma 10 is 2. Sorry, is 5. Phi of AB is equal to phi of A into phi of B. So how do we prove this? Like if A and B are coprime, then phi of A equal to phi of A into phi of B. How do we prove this? We prove this using Chinese remainder theorem. Okay. How do we prove it? Okay, before I forgot to prove the exclusiveness of Chinese remainder theorem, let us say x equal to a1, x equal to a2, mod n1, mod n2, x equal to ak, mod nk. We know that only one such x exists. How do we know? Let's try to prove this by contradiction. Let us say there exist two numbers p and q which satisfy this equation. P equal to a1 mod n1, p equal to a2 mod n2, p equal to so on up to p equal to ak mod nk, q equal to a1 mod n1, so such that p comma q both are less than n1 capital N. Capital N is the product of all the n1, n2, n3, nk. If there exist two such p and q less than n, then p minus q, what would this be? This mod n1 is equal to a1 mod, the p mod n1 is a, q mod n1 is a1, so p minus q mod n1 will be 0. Similarly, every equation p minus q mod nk would be equal to 0. That means p minus q is a multiple of n1, n2, n3, so on up to nk. Then p minus q mod n should also be equal to 0. Since p minus q divides n1, divides n2, so on up to nk, p minus q should be a multiple of capital N. Since p and q both are less than n, such a pair can exist only if p is equal to q. If p is not equal to q, p minus q will not be equal to 0. So we proved that there exists only one such pair p comma q. Sorry, exists only one number p which satisfies all these numbers. So since we proved the exclusivity of Chinese remainder theorem, let's write x equal to a1 no, sorry, let's write x equal to d1 mod a y equal to x equal to d2 mod b this means that d1, let us say that d1 is coprime for a and d2 is coprime for b, then x is coprime with a, then x is also coprime with b, then x will be coprime with a into b. GCD of x comma ab will be equal to 1. If d1 is coprime to a and d2 is coprime to b, then GCD of x in comma a into b will be equal to 1. This is because since d1 is coprime to a, x is coprime to a. Since d2 is coprime to b, x is coprime to b. And hence, x is coprime to a into b. Since we already know that d1 and d2 pair can correspond to only one coprime to ab, number of such pairs will be equal to phi of a into phi of b. There are phi of a number of d1s, there are phi of b number of d2s. Each d1 d2 pair corresponds to one coprime of a and b. Such that way LHS will be equal to RHS. Let's go further. If p is prime, phi of p is equal to p minus 1. It's very simple. There are no numbers which have a common factor, right? Somebody just asked, please repeat last step. Do you want to have last step repeated? Please select an answer. Select a true if you want to repeat the last slide. If you want me to repeat last slide, please select true. Okay. A lot of people want me to repeat the last slide. Okay. Is this part clear? Is this part clear that if given a1, a2, a3, so on up to ak, there exists only one such x less than capital N which satisfies these equations. K equations are satisfied by only one x less than n. Okay. Now, let us say there is an x less than ab, a into b, whose GCD is equal to 1. Since x is a coprime for a into b, x is also coprime with a. d1 will also be coprime to a. Since x is coprime to a into b, x will also be coprime to b. Since that way, d2 will also be coprime to b. So each pair d1, d2 corresponds to only one x less than ab. Right? Since we just saw that every tuple a1 to ak corresponds to only one x, only one p, every pair D1 and D2 corresponds to only one X which is co-prime to AB. So number of such pairs D1, D2 are phi of A into phi of B. D1 is a co-prime to A. How many such numbers are there? Phi of A. D2 is co-prime to B. How many such numbers are there? Phi of B. So for each D1, D2 pair, there exists an X which is co-prime to AB. Got it? Is this clear? Oh, great. Okay. For a prime P, the Euler totient function will be P minus 1. There is no number X less than P whose GCD is greater than 1. That is the definition of prime, right? There are no factors of prime. Any questions so far? Got it. Let's move further. So we are going to take a look at Fermat's little theorem as well. So for two numbers A and P, where P is a prime P is prime, then A power P minus 1 is equal to 1 mod P. Is this clear? A power P minus 1 is equal to 1 mod P. Fermat said this when he was alive, but he did not give any proof. But still, let's try to prove this. Like, this means that A of P minus 1, if we take modulo P, the remainder will be equal to 1. Fermat said this, I did not say that. Let's try to prove it. Okay, the proof of this would be simple. Let us say, let us take a look at this. A into 1 plus, sorry, A into 1, A into 2, so on up to A into P minus 1. Let us take a look at all these P minus 1 numbers. There are P minus 1 numbers. The first number is A, second number is 2A, third number is 3A, so on up to P minus 1th number is P minus 1 into A. Now, since A and P are co-prime, A into I will not be equal to A into J mod P. I and J are less than P. This cannot be valid, right? For if I not equal to J, then A into I will not be equal to A into J mod P. The remainder we get after we divide A into I will not be equal to the remainder we get after we divide A into J with P. How do we prove this? I'll leave it up to you. If I not equal to J, then AI not equal to AJ mod P. I would like you guys to prove it by yourself. It's very simple. You can prove it by contradiction. Then let's try to multiply all these numbers. A1, 1A into 2A into 3A so on up to p minus 1 into a. Since ai not equal to aj for I and j, different I and j, every a 2a 3a so on up to p minus 1a, each of these correspond to some number between 1 2 3 so on up to p minus 1. Maybe this is equal to some 4, this is equal to some 2, this is equal to some 7, like that. Each number corresponds to one distinct number between 1 and p minus 1. So this will be equal to 1 2 3 so on up to p minus 1 mod p. Since the terms 1, 2, 3, so on up to p minus 1 are common, we can cancel them out. We get a power p minus 1 equal to 1 mod p. Hence proved. There it is. I would like you guys to write down these things in your notes. I'll quickly drink some water and come. Then I'll continue the class from there. Till now, whatever we have, try to revise those things. From there, we'll go. I'll just be back in 2 minutes. I am back. Somebody asked, is that space wallpaper on your ceiling? Yes, it is. Do you like it? Thank you guys. Yeah. So there are some resources mentioned here. So when you guys have time after the class, like please go through these resources. You can learn a lot from there. Like especially the first link here. the emaxru.algo. This link is like a really good link. The algorithms that are explained there are like really simple to understand, and there are long list of algorithms there, so you guys can understand a lot there, like, learn a lot there. And for Fermat's theorem or Euler function, like you can go through these resources, and for Chinese remainder theorem and GCD, uh, they are like that. So so far, let's please send the PPT to Discord. Sure. After the class, I'll post the link to the PPT in the Discord. Uh, how about this? Like, uh, I'll try to summarize everything that we have learned till now, and then we'll solve some problems based on whatever we learned till now. Okay. First link is not in English. Yes, it's in Russian, but you can use Google Translate, or Yandex also has a really good translation. But I think like some algorithms Yandex was better, and some algorithms Google was better. Like you can just right click and translate to English in Chrome. So in Microsoft Edge, if you are using Edge browser, then the uh, Bing translation is very bad. I tried it, but Google translation was very good. Yandex is probably the best. Oh, cpalgorithms.com. Is it the same? Uh, oh, okay. Looks like the same. Yeah. Okay. Abhishek just shared the English version. It looks like the same. Thanks, Abhishek. Yeah. So let's go to the beginning and see. Let's have a. Yeah, I'll try to summarize everything from the beginning once. So, what did we learn? We learned the modular operation. A mod n is equal to the remainder we get after dividing with n. We learned the modular representation. A mod n is equals to b, then we write a equal to b mod n. We also have learned what are the integer factors. The integer factors are just the divisors. You say like the numbers which divide and whose multiple is n. We also wrote the representation as n equal to 0 mod a. If we divide n with a, the remainder is 0. GCD of a pair of integers, it's the largest x such that a equal to 0 mod x, b equal to 0 mod x. The largest number which divides both a and b. We also learned the coprimes where GCD of a and b is 1. Now we learned the Euclid's theorem to find GCD, uh, which was, suppose you know the GCD of a comma b mod a, that will be equal to GCD of a comma b. So recursively we can do this, right? Like suppose we have, let me uh, let me try to write some code here. uh, you guys can see my screen, right? So let's get it. Well, let's use idea. Let's just use idea. Dark Knight, yes, you can use GCD of the inbuilt function. Sure. That's okay. My laptop is hanging if I am using more than one tab. Sorry, guys. I'll try to type it out here. GCD of, you can write a function GCD AB equals to GCD of A comma B mod A. Right? We can write a C++ function like this. Int A comma int B return A if B equals 0, B equals 0, return A else return GCD of A comma B, something like this, right? We can recursively find the GCD of A comma B using that way. Then we also learned about Bezoart's identity. If D is the GCD of A and B, then AX plus BY equals to D. We can find such an X and Y. We used Euclid's algo, extended Euclid's algo to find the pairs X and Y. That we did. First we found the exponent y1 for B mod A comma A. Then we used exponent y1. We used exponent y1 to find x2 and y2. It's reverse. It's y2 and x2. I made a mistake. We used we found exponent y1 and then we found x2 and y2. Next, we learned about linear Diophantine equations. These are possible only when GCD of A and B is a divisor of C. When does the solution exist? Only when GCD of A comma B is a divisor of C. If GCD of A comma B is G, then CG. We found that. We learnt about inverse modulo. We found inverse modulo using Euclid's extended algorithm. We learned about Chinese remainder theorem. Like there are k integers a1, a2, a3, so on ak, and we have k other integers a1, n1, n2, n3, so on nk. There exists only one such x which satisfies all these k equations, and we proved and we found how to find those. We also found Euler totient function. Okay, one thing we can do is for any given general number phi of n which is not prime, the Euler totient function will be n into 1 minus 1 by p1 into 1 minus 1 by p2, so on 1 minus 1 by pk, where p1, p2, p3, k are all the prime factors of n. So given that, then phi of n can be written like this. I would encourage you guys to prove it by yourself how we get this. Somebody just asked in the code I wrote GCD if A is 4 and B is 2. So that assumes that A is always less than B, Majabin. If A is greater than B, then we just swap A and B, like before performing any operation. We learned the Fermat's little theorem. It says that a power p minus 1 mod p will be equals to 1. If we divide a power p minus 1, the remainder when we divide it with p is equal to 1. That is true because of a long proof. I would suggest you guys to go back in the video and watch it again uh, to understand that. Here are some resources and let's try to solve a problem. Given an integer n, find the smallest m such that m by phi m is maximum. I'll give you like 2 minutes to think about this. Given an integer n, try to find n such that m by phi m is maximum. No, that's not the right answer, Kaushik. So So what is m by phi of m? We just learned about that phi of m is equal to m into 1 minus 1 by p1 so on up to 1 minus 1 by pk. So if m by phi m is 1 divided by 1 minus 1 by p1 so on up to 1 minus 1 by pk, where p1, p2, p3 so on up to pk are the prime factors. So this will come out as P1 by 1 by P1 into P2 by 1 minus P2, sorry, P2 minus 1, P1 minus 1, P2 minus 1, P3 by P3 minus P3 minus 1, so on up to Pk by Pk minus 1. So this thing will be maximum for what numbers? Like this number will be greater than 1 for sure. If we take two primes, some, let's say 17 and 31. 17 by 16 will be greater than 31 by 30. This is because this is equal to 1 plus 1 by 16 greater than 1 plus 1 by 30. 1 by 16 is greater than 1 by 30. Hence, 17 by 16 will be greater than 31 by 30. So, if there any like we for any two pairs, two primes, P1 and P2, we always try to pick the smaller prime first because it will give a bigger answer. And the solution will be just be 2, this will be 3, P3 will always be 5, P4 will always be 7, so on up to Pk. The product by 1, 3 by 2, 5 by 4, 7 by 6, Pk by Pk minus 1, Pk minus 1. We find like maximum such prime less than n. That will be the answer. So let's try to add a slide. How do I add a slide? Add a slide. Okay. Is the answer clear to you guys? The previous problem. Does anyone want? Is the answer clear? I'm just creating a poll. If you guys select false, I'll try to repeat the answer, or else we'll solve a different problem. Okay. Does the poll happen? Did the poll happen? I can't see the results of this poll. Okay. Was the answer clear for the previous problem? I'm not able to create a poll. Can anybody hear me? Hello? Hello? Can anybody hear me? Hello? I can't see you guys. I have to refresh this, I guess. I just refreshed my page. Can somebody please ping in chat if you can hear me? Okay, great. Somehow my laptop got stuck and I could not hear you guys or see or any of your messages. Okay. Uh, were you able to understand the solution for the previous problem? Uh, okay. Somehow this will. Let's try to solve one last problem. Okay, I'm not able to write this. Okay, I am pasting a problem link in the chat. Sorry guys, my laptop just is working very slow. I am not able to do it fast. I'm not able to see your guys' responses. Yeah. Can you guys open this problem? Guess prime on CodeChef and see the problem. We'll try to solve that problem and Looks like we don't have much time to discuss that problem. I found a different problem than uh, it's not very easy or intermediate. So we'll not be able to discuss that problem here. So if you go to CodeChef and search for number theory problems, there are a lot of problems on this category. So I'll try to take another class to solve the problems based on this. So I hope you guys learned something new today. So you can go to CodeChef and uh, use this knowledge and solve the problems. So Rahul, I think we are nearing the end of the class. So if you can please go back to the mm, previous uh, like few minutes. So like you can repeat the whole stream. The stream will be available on Academy. So yeah. Uh, no, we have to use Chinese remainder theorem in that problem. I don't know which problem you are talking about. So yeah. Hence, do you guys have any questions, like any general questions regarding the class or anything? Slides will be available in an academy. I'll also paste the PDF link to uh, Discord server. So, is it necessary to remember the proof? You don't need to remember the proof. Like, if you understand the proof, then like you don't need to remember it. Like any general mathematical proof, you can just try to solve it again in future. So you don't need to worry that you need to remember these. But once you solve that problems again and again, then you will remember the proof. Is it okay to do CP on any one platform like CodeChef or CodeForces also a must be? Uh, I would recommend doing on both because CodeChef does not have uh, like it only has four big contests, right? Like if you want to solve more problems, then doing CodeForces is also better. I would suggest doing live contests more because that will actually test the skills that you gain. Uh, how to handle 10 power 40? 10 power 40 is just uh, wait, 10 power 40, you can handle it using two long longs or three long longs, right? Like there are some libraries available uh, for big integers in Java, or like you can write on your own things, right? It should not. It's not a big thing. It's not hard. Um, are glasses comfortable to wear? I mean, you get used to it after a while. Initially, it might be a little less comfortable, but yeah. Game theory slides 2. Sure. I think there is some bug in the Unacademy website. They should have been available in the website link, but I'll paste them there too. Uh, in the beginning, it's better to write it from scratch, Zakir. Uh, a little later, you can reuse. But if you are learning to code, then it's better. What's your startup? Sorry, I cannot discuss about it here now. What's your rating? What rating is good on CF to put on your resume? Think anything high orange is probably good nowadays. Other ratings, I think, doesn't matter if you put it or not, to be honest. How much time to do daily? I'm not a really good person to answer this question because I never used to manage my time. Like I used to do as much as possible. Can number theory in pure maths help in competitive programming? Yes, definitely. There are a lot of problems uh, which use number theory. Uh, Let me extend this by a few minutes. Uh, okay, so there's that. I'll try to send the PPT links to Discord server. I hope you find there. Yeah, thanks guys. It was fun teaching one of my favorite topics. Thanks for your guys' presence. I liked it. I hope you guys enjoyed it. Bye bye.